Today's lesson is graphs of polynomials, and we will not be using a calculator. So let's review today's learning objective. I can graph or state critical attributes of polynomials by analyzing the leading term, zeros, and y-intercept without a calculator. If I remember all of this from Algebra 2, I would classify myself as an expert. If I remember nothing, I'd say I'm a novice or I'm somewhere in between. So let's just kind of get an idea where we are before we start. All right, we're going to start with some vocabulary here with defining what a polynomial function is. So a polynomial function is the sum of power functions. And then let's go through some vocabulary. I have a polynomial listed here. Let's begin with each monomial in the sum. So each monomial, so I have 1, 2, 3, 4, 5 monomials. So one monomial is 2x cubed. The next monomial is minus 3x squared, 6x to the fourth, negative x, and 5. So these are each a monomial. For standard polynomial form, we write the terms in descending form. So I start with the highest and go down to the lowest. So this would be f of x equals 6x to the fourth plus 2x cubed minus 3x squared minus x plus 5. Coefficients are defined as the numbers that are next to a variable. So the coefficients I have are 6, 2, negative 3, and negative 1. My leading term is the term with the highest power. So this is 6x to the fourth. My degree is the highest power, so my degree is 4. And my constant term is my number without the variable. So my constant is 5. We did an end behavior investigation in the last unit that focuses on what the leading term is. So I'm interested, I know a lot of information from the power, and I'm looking for the power. I'm looking, is it even or odd? And I am looking at the coefficient here, and I want to know, is it positive or negative? It tells me a lot of information from the leading term. So we'll come back to some of that. All right, so let's start with identifying what a polynomial is or not is not a polynomial. And if I know that it is a polynomial, I want to state both the degree and the number of terms that I have in that polynomial. So let's start out with number 1. F of x equals 3x to the fourth plus 6x squared minus 5. This is a standard polynomial, so I'm going to say yes. And my degree, I'm looking at the highest power, is 4. And I have 1, 2, 3 terms. Okay, number 2. F of x equals 2 times the square root of x plus 8. I could rewrite this and say this is 2x to the 1/2 power plus 8. And by definition, all the powers have to be positive whole numbers. So no, this is not a polynomial. The power is not a positive whole number. Okay. Number 3, f of x equals 3x to the -4th power plus 6x squared. So we just talked about, we just talked about that I need to have positive whole numbers for the power. So no, again, so there's no negative powers. Number 4, f of x equals 3 divided by x minus 5. I could rewrite this. When I move a power from the denominator to the numerator, I change the sign. So this would be 3x to the -1 minus 5. So again, I have no negative powers. Number 5, f of x equals x divided by 3 minus 5. So this one is a polynomial. So yes. And my degree, this is x to the 1st power, so my degree is 1, and I have 1, 2 terms. Okay, number 6, f of x equals 3x to the 4th plus 6x minus 5 divided by the quantity x squared minus 4. A polynomial does not have a denominator, so no, because this is a rational function, not a polynomial. That'll be our next unit. All right, let's look at number 7. F of x equals 5x times the quantity x minus 3 squared. Okay, I'm going to expand this out. So this is really 5x times x minus 3 times x minus 3. Okay, I'm doing my distribution here. I have x squared minus 6x because I have minus 3x and a minus 3x. Combining like terms, I have minus 6x plus 9. Distributing across all my terms, I now have 5x cubed minus 30x squared plus 45x. Okay, so looking at my function, I say, yes, I have a polynomial. I'd say my degree, looking at the highest power, is 3. And my terms, I have 1, 2, 3 terms. Hang on. There we go. Okay, so reviewing from the end behavior we had from the last unit, and I'm looking at the leading coefficient. So let's take a look. So on this one, I'm looking at the degree. I want to know, is the degree even or odd? This is the power. And I want to know if the coefficient, the number in front of the variable, is positive or negative. So taking a look at whatever my leading term is, so this is my leading term, I'm going to just draw an arrow. So if I have a leading term where I have an odd power, so I'm going to think of linear to start out with. I know just thinking about a linear function, that means I start at negative infinity and I end at positive infinity. So I'm thinking about y equals x here. So for an even power, I'm thinking about a quadratic. So I'm thinking about y equals x squared. So, oh, and I'm drawing this in the wrong spot. I'm sorry. So if I have a positive coefficient, I begin at negative infinity and end at positive infinity. So if I'm talking about y equals x squared, I'm beginning and ending at positive infinity. So if I just change the coefficient from positive to negative, I'm doing an x-axis reflection. So I would start at positive infinity and end at negative infinity. And here I begin and end at negative infinity. So I know when I have odd powers, I begin and end different. If I have even powers, I begin and end the same. And if I don't remember this from the investigation, I can just type a few of these in my calculator and see. So let's just check. So if I'm looking at x squared, and I have a positive coefficient and an even number, I'm beginning and ending in positive infinity, no matter how many powers I have, as long as I'm even. If I have a negative coefficient, I'm beginning and ending at negative infinity. So if I have odd powers and an even coefficient, if I begin and end, I begin at negative infinity and end at positive infinity for all positive coefficients. And I begin at negative infinity and end at positive infinity. I begin at positive infinity, end at negative infinity for an odd coefficient. So just if I keep adding numbers to the power, when I notice, and it doesn't matter whether I have even or odd functions, I see that the curve becomes narrower. Oops. Narrower and flatter the higher the power becomes. And it doesn't matter whether it's an even or an odd power. All right, so with that said, let's start graphing a few of these polynomials without a calculator. All right, so if I have number 11, f of x equals the quantity x minus 2 times the quantity of x plus 3, I want to graph this. So to graph it, I need information. I need to know what the degree is, the number of real zeros, what the zeros are, what the multiplicity of each zero is, what the y-intercept is. I want to be able to describe my end behavior, and I want to know what's the number of relative extrema. Once I have all that information, then I can graph my polynomial. Okay, so I'm going to start out by, I am looking at, I need to do a double distribution to multiply this out so I can see what the leading term is. So this is going to be x times x is x squared plus 3x minus 2x minus 6. So looking at the degree, I get the degree from the highest power, so my degree is 2. So I can get my number of real zeros by, I can see the factored form, and I can add the power of the factors. So I have 1 plus 1 is 2, or I can see that from the power here. So I know I have 2 real zeros at most. Then I can set each factor equal to 0. So I would say x minus 2 equals 0 and solve for x, and I get x equals 2. So x plus 3 equals 0, and I get x equals negative 3. So when I want to list my zeros over here, I want to list them from least to greatest because that helps me for the graphing. So my zeros are minus 3 and 2. Now the multiplicity means how many times that occurs. So I'm looking at the factor. What is the power of the factor? So for the factor x plus 3, I'm raising it to the power 1. So I have a multiplicity of 1. Same thing for the factor of x minus 2. I'm raising it to the power 1. So I have a factor of 1. My y-intercept, I got that from my constant term. So my y-intercept is minus 6. My end behavior, I get that by looking at my leading term. So I have a positive coefficient and an even power. So I know I begin and end at positive infinity. And the number extrema, I'm going to be looking at the graph to do that. So to plot my graph, I am going to first plot my zeros. So I have minus 3 and 2. Next, I'm going to put in my end behavior. So I know I begin at negative infinity and I end at negative infinity. And I know that my y-intercept is at minus 6. So I'm going to just say this is minus 6. So I want to know where the zeros are and where the y-intercept is. So I know I need to come down and return back up. So taking a look, I see that I have one minimum. So I have one minima. All right, that was not too bad. Let's try another example that adds some more details. All right, so I have f of x equals x times the quantity x minus 4 squared. So the degree on this, I can find the degree by adding the powers. So I know this is x to the first power, and I know if I multiply x minus 4 times x minus 4, I'm going to get x squared. So the power is, I am adding these powers here, so my degree is 3. So the number of real zeros I have are 3. So I'm adding the zeros. So I have a 0 here. So another way of writing this as x is really minus x minus 0 times x minus 4 and x minus 4, right? So I can see I have a 0 at x equals 0 and x equals 4 and x equals 4. So writing these from least to greatest, my zeros are 0 and 4. I can see the multiplicity is the power that I'm raising the factor to. So I'm raising x minus 0 to the first power. So I know I have a multiplicity of 1. And x minus 4, I am raising to the second power. So I have a multiplicity of 2. My y-intercept, if I multiply all the constants together, I would be multiplying 0 times negative 4 times negative 4, which is 0. So my y-intercept is 0. My end behavior for my leading term, so I would be multiplying out all the x terms. So I would really be multiplying 1x times 1x times 1x. So my leading term is 1x cubed. So I know my coefficient is positive. and my power is odd. So I'm thinking about a linear equation. So I know I begin at negative infinity and I end at positive infinity. So to graph, I put my zeros down. So I have a 0 at x equals 0 and a 0 at 4. Next, I'm going to put in my end behavior. I know I begin at negative infinity and I end at positive infinity. I know that my y-intercept is 0, so I already have that. And then to draw in the rest, I'm going to add what I know about the multiplicity. So the multiplicity means that if I have an odd multiplicity, I am going to cross the x-axis. So I know I'm going to continue up. If I have an even multiplicity, I'm going to bounce. So I'm not going to cross. So to draw in the middle, I'm going to cross and then bounce, and I'm getting that from the multiplicity. So to ask my last question, how many extrema do I have? I have a maximum here, and I have a minimum here. So I have 2 relative extrema. So I get at the minimum, at this double root, I'm going to call that a double root. At a double root, I bounce. And on a single root, here I cross the x-axis. So I need to know when I'm crossing and when I'm bouncing. Okay, last example. Let's do a different color. So last example. F of x equals negative quantity x minus 2 cubed. So if I need to give myself some hints, I'm going to say this is negative 1 times x minus 2 times x minus 2, x minus 2. So adding up all the degrees, I have 1 plus 1 plus 1 is 3, or I could have seen that right here. So I know my degree is 3. So the number of real zeros I can have is 1, 2, 3. If I am solving each factor, this would be x equals 2, x equals 2, x equals 2. So the zeros I have are just the number 2. My multiplicity is, I have it by raising it to the power 3, or if I expanded it out, I can see I have it 3 times. So my 0 of 2, I have 3 times. So I have a multiplicity of 3 for the 0 of 2. My y-intercept, I would take the constant. So I'm gonna multiply this negative 1 times negative 2 times negative 2 times negative 2, which is positive 8. So negative 1 times negative 2 times negative 2 times negative 2 is 8. My end behavior. So what does my leading term look like? This would be negative 1 times 1x times 1x times 1x. So my leading term is negative x cubed. So now this is negative. So my coefficient is negative and my power is odd. So my end behavior, so I'm thinking of a linear equation, but since I have a negative coefficient, that means it's an x-axis reflection. So I start at positive infinity and I end at negative infinity. Okay, so let's put our zeros in. So our zeros are at x equals 2. We said our y-intercept is at 8. So I'm going to draw in 8 up here. I'm going to draw in my end behavior. So I know I begin at positive infinity. So I know I have to keep going this way. And I am ending at negative infinity. So taking a look, I have neither a minimum nor a maximum. So I can have no extrema. So at this point, I see this is a triple root. Okay, so this is a triple root. And what I see is, if I really look closely, it kind of changes curves. And if you see this curve here and this curve here, they're going the opposite direction. So it's changing what's called the concavity. And we call that an inflection point when I change concavity. So my inflection point. And if I look at it, so this is an odd power. So odd powers go across the x-axis, even powers bounce. So let's summarize a little bit what we know about polynomials now. So a polynomial, by definition, is a smooth and continuous curve. It has no breaks, gaps, holes, or sharp terms. The domain is from positive infinity or negative infinity to positive infinity, so that means it's all real numbers. My end behavior is the same as the power function of the same degree. Has at most of a degree n has at most n roots. So for a single root, that means I'm going to cross the x-axis. Okay, so it doesn't matter. I can cross it from negative to positive or positive to negative. If I have a double root, I'm going to bounce on the x-axis. So that means if I'm coming from the positive infinity, I would look like this. If I'm coming from the negative infinity, I would look like this. So this has to really do with any even root. And a triple root also crosses. I guess I should say crosses the x-axis. But it's kind of curvy. So if I'm starting at negative infinity and going to positive infinity, or positive infinity going to negative infinity. So that one's an inflection point. Okay, that's the end of the lesson.